Hi, welcome to Neuroverse, a podcast hosted by Carolina
and Clara, where we discuss all matters from neuroscience to philosophy and beyond.
Today's episode is about dynamics of strategy learning of deep neural networks. And to help us with this topic, we are joined by Aditya Singh, who is carrying out a PhD on learning dynamics of various strategies and circuits in deep neural networks in Professor Andrew Saxe's and Dr. Felix Hill's lab at UCL in the Gatsby Computational Neuroscience Unit. Aditya completed his bachelor's and master's in MIT on computer science and neuroscience, and then Aditya went on to work in DeepMind and Meta before starting his PhD. Welcome to the podcast.
Thanks for having me. Happy to be here.
Awesome. It's great to have you on. Why don't we start in the beginning and let us know why you got interested in neuroscience in the first place and computational neuroscience and how that led on to your PhD?
Yeah, sure. Yeah. So I guess this might sound kind of cheesy, but I still remember the first time, I think I was in second grade when I learned the concept of neurons and the brain, and it I don't know, maybe kids don't think about it, but I never realized all of me as I perceive it is actually just this little piece in my head. And it's specifically interestingly made up of these small neurons that each do something very basic, right? Obviously, as a second grader, you can't really pursue neuroscience, so I didn't for a while. Next exposure was 5-6 years later. I was doing some science competition which had a neuroscience section, so I read a textbook, so that was kind of cool. But then I really say high school, I was lucky to go to an accelerated high school, and so they had an artificial intelligence class which I was able to take. And then the last unit in that class was on deep neural networks, of course, right? But this was still in 2015, so they were getting there, but not that popular yet, right? And there it just hit me because I guess I do a lot of math and computer science, and so then that just felt like the perfect combination of the two. And then when I went to MIT, obviously they have really good classes in this direction, so I was able to luckily have a lot of nice classes at the intersection. It was pretty easy for me to double major because a lot of those classes could count for both, and so I think the department generally also wanted more people to be doing this, and so I was cool, yeah. And then now I'm here, I guess.
Awesome. And can you tell us about your PhD research?
Yes, yeah. So I guess I can start with why, and then go into kind of what I work on.
Yeah.
So I guess why is also for me very much important to pick something that I wonder about in my daily life, because I think that helps me stay motivated, which is hard in a PhD, right? And then so I play a lot of board games, actually. This is where it all started for me. And actually, if you read my statement of purpose, it starts with the sentence, I love playing board games. And
yeah, I have to say, when I first met Aditya, it was also my first day in SWC, and we were playing, what was it,
I think
Scrabble?
It was Bananagrams.
Or Bananagrams? Oh my god, Aditya is the best person I've ever seen playing Bananagrams, and I was so intimidated, and I was what kind of institute did I just walk into?
Yeah, and I remember you telling me this.
Yeah.
And all I've known about you so far is a person who likes games and understanding how to get better at them.
Yeah.
Yeah, so I do really enjoy games, yeah. And specifically for me, the coolest part of games are right after you learn, seeing people come up with strategies and iterate. I think even by the end of the first or second game after playing, humans are really good at already developing some of the near optimal strategies, right? Or as optimal as we know, I guess. And so I find that very fascinating, and artificial agents, at least so far, are not capable of doing this. For example, even GPT-4 can't really play tic-tac-toe, right? Which is pretty bizarre. And so I'm really interested in how do humans actually acquire these strategies so quickly, and can we maybe make agents that acquire strategies at a similar pace? And I think a really key aspect towards that goal is understanding the learning dynamics. And the reasoning behind this is kind of, so far, when people try to understand deep neural networks, they often just focus at the end of training. What has the network learned to do after you finish training it, right? You could argue in neuroscience, similarly, we'll often train a mouse and then just look at how it's performing the task. But I think to really figure out how we need to edit these algorithms for learning in neural networks to be more like humans, we would actually want to match the learning trajectories of humans. That requires understanding learning trajectories on both sides and then pushing forwards to connecting the two. And that's what led me to what I work on.
Yeah.
Nice. So before the podcast, you were telling me about how you have quite a few projects within your PhD, but what is your major focus kind of addressing?
Right, yeah. So it's, I guess there's two projects. I think what unifies them is basically looking at how various strategies are learned by deep neural networks. One of the projects will also look at humans, but I would say the real unifier is kind of these strategies. And I know strategies might sound a bit abstract, so I can explain kind of an example of those.
Yeah.
So, for example, on the side of board games, an example could be something as high level as an attacking or defending strategy, but also something more lower level, for example, in the game of chess, right? You have different pieces, you move the pieces, you can capture other pieces, right? And so in chess, there's this notion of protection where piece A might be protecting piece B. And the kind of idea there is that if something captures piece B, piece A will recapture, right? And so that's a very simple concept humans tend to develop. It would be interesting to see, and kind of how it's applied as, that means you shouldn't move piece A, right? Because then piece B is unprotected. Mm-hmm. And so that's kind of an example on the board game side. On kind of the other side of my PhD, more with deep neural networks, especially in the current realm of language modeling, the main concept I've looked at is this thing called in-context learning, which is the ability that these transformer language models have to learn from what you tell them. You could teach them a new word, and they'll start using the word. And that makes these models very customizable. It makes them usable by so many people, right? And so I've been looking at the dynamics of that strategy emerging throughout the training process and understanding why it occurs. Does it stick around? Are there risks of losing it? How could it be more robust? Things like that.
So my first thought was that a lot of how you're able to perform in a game is how you understand the rules or interpret the rules. So is there a difference in how humans versus these artificial neural networks can integrate that information and understand the rules? And because I was thinking about how our ability to improve over time may also be understanding the rules in the context of our moves and our actions.
Yeah, that's a great question. So that's definitely a huge factor, especially for a lot of board games. And the way people typically train neural networks is you don't actually tell them the rules, you just kind of let them do things. And whenever they make an illegal move, you don't let them do that. And so the network is kind of playing the game, but also learning the rules, weirdly. And so it's not super clear how you can actually give kind of text input and start getting moves out, right, in an actual board game state. And so to kind of circumvent the issue, we've tried to focus a bit smaller scale on puzzles. So you could think like a Sudoku, right? And there it's actually pretty simple to explain the rules, right? Yeah. And so Sudoku comes from this family of puzzles called Nikolai puzzles. And we've picked this other one called Star Battle. And we're studying that one, and because the rules for that are they take less than a minute to explain. So there's not really any lack of clarity there. And we believe also the network will be able to learn the rules relatively quickly, and then we can actually look at kind of the concept formation. Yeah.
Okay, nice. And have you managed to improve how well they perform in these puzzles?
Right, so so far we've just been focused on understanding and kind of building up all the infrastructure on that side. Yeah. The puzzles project has been on a bit of a pause because I've been working on the in-context learning things recently.
Right,
yeah.
Okay.
This is kind of a random question. Given that you studied so much about board games and how to get AI to learn the rules and things, has that kind of ruined board games for you a little bit? Because it's only a 3-step process before you get the rules. It's not complex enough,
But I was also going to ask if it has helped you improve your strategies.
Yeah, so I don't think it's ruined board games for me. This was a concern going into my PhD. I was if I start doing board games as part of my research, will it ruin it? I'd say in some ways it's actually helped because when you play board games, you're not getting work done really, right? And board games can often be quite long, but since my PhD is now related to board games, it's like kind of working, right?
That's
Especially
why they say to make your life your work.
Passion your work.
Passion your work, yeah.
Not your life, your work.
Yeah,
But yeah, in terms of the other way, I think the board games I tend to play these days are kind of so far beyond what our current AI systems can do that there hasn't been that much transfer. But I think in other ways, like, I think one way in which my board game playing has changed is a bit motivated from reinforcement learning. So in reinforcement learning, there's this concept of a value function, right? Where you assign values to different states, and then when you're choosing an action, you kind of want to pick the action that leads to the state with highest value, right? So when we train a neural network, like a reinforcement learning agent to play a board game, part of what it learns is this value function typically. And some people work on understanding, well, what features is this value function looking at in the board game, right? And so there's this really interesting work on chess and looking at that network, and then they actually were able to regress out the values that the network is giving to different pieces in the board game. And these values are actually quite close to what human chess players are taught.
Yeah.
Right? Like knights and bishops are worth 3 points, rooks are worth 5 points, and so forth. And so I thought that was really inspiring. Nowadays, when I play board games, I do take this more like, not like it's hard to necessarily assign a value to the whole position, but to like many actions or like subcomponents in the game, I'll often be like, oh, well, I know if I like play this card that costs $10, but it'll produce $5 each round, so in 3 rounds, I'll start making a profit, right? And then if I know the game will go for 5 rounds, then the total profit from playing this card is $15, let's say. And then I might compare that against playing other cards. And so not quite what the neural network would do, but there is some high-level connection, I'd say.
Cool. Wow. Going back to strategies of learning, you have this paper where you talk about how sometimes the optimal point in learning is not like the end of training, it's a bit before. Can you tell us a bit about that? Yeah,
so this was some really cool work. This is kind of what led me to pivot a bit for a while onto in-context learning, where, like I mentioned earlier, in-context learning is this ability that language models have that is pretty desirable, right? Because that's what makes them useful to so many people. And so we had done some work on trying to understand where this ability is coming from. This is back when I was at DeepMind. And basically what we did is, we know that when you train a big model on language, you get this ability. And we wanted to see what features of language are important for that. So we created synthetic data sets. We found that certain properties of language, when you insert into these data sets, boost this ability's appearance. And so one day I was just like kind of going through the results of that paper, and I noticed that like the curves were kind of like tilting downwards slightly at the end, which I found kind of surprising. And we'd been trying to work out some theory on like why these data properties asymptotically lead to this circuit emerging, and the theory wasn't working. And so a part of me was like, well, maybe it's not asymptotic, you know? And so I told one of my collaborators, I was like, could you just like run this for a month and like we'll see what happens? And turns out the ability goes away. And so this is very interesting, where basically if you keep training a network for longer, it's still generalizing, but it's completely switched the strategy that it's using to solve the task. And this is very surprising. And we don't still quite understand why, but we've started to dig into why. And so that's kind of what motivated, earlier I was talking about like how we could maybe make systems better by understanding learning dynamics. Here it's kind of like necessary to understand the dynamics to keep them from getting worse almost, right? We don't want this ability to go away. And so we've been trying to understand like the dynamics of this ability emerging, to which end we've kind of identified, rather than having to wait for the whole ability to show up, which kind of, it happens in what's known as a phase change, where kind of the network's not performing the strategy and then it starts performing it all of a sudden, and then it slowly goes away. We've been trying to understand what leads to that leap of kind of understanding all of a sudden. It turns out that there are kind of simpler circuits that are being composed to create the strategy, and each circuit on its own learns smoothly, but the issue is that you kind of need all the circuits to line up in order to learn. And so the reason you have the sudden jump is, before that sudden jump, they're kind of just aligning, and then once they're aligned, you learn very quickly.
Interesting.
So yeah.
It's kind of like a meta mechanism.
Yeah, exactly.
Yeah.
And so we're also hoping with that, like, obviously we just looked at in-context learning, but we're hoping that a lot of the techniques and kind of toy models we propose in that paper, just this kind of framework of thinking about learning dynamics, might be useful for other abilities in language models that kind of sometimes appear, sometimes don't, and understanding those, yeah.
Wait, so if I understand correctly, you said if you train it for a really long time, like months, did you say?
Or like, well, I guess it depends on the hardware you use, right?
Yeah,
And
okay,
depends on
yeah.
the model. You can reproduce it in pretty small settings as well, once you know the key factors. Yeah.
But you said it switches strategies.
Yeah.
So is the strategy it switches to like less efficient, or?
So the strategy it switches to, our intuition is that for the network, it's actually more efficient in some sense. Like, clearly the reason it switches is because it's just trying to minimize its loss, right? And somehow this other strategy, even though both strategies can get 100% accuracy, one strategy might be able to be more confident in its answers, which is going to reduce the loss. And so the network will switch to this other strategy, and the reason that's bad is because we want it to do strategy A. The reason it switches is because language doesn't require you to do in-context learning, right? It's just, it so happens that, at least our hypothesis, it so happens that on the path to the optimal solution, you always get this ability, and that's actually the ability we want. And so now we want to think about, like, yeah, why does it show up at all? Yeah.
Wait, why does learning language not require in-context learning?
Well, given how large models are becoming, a model could just memorize every single string in its training data, right? And then it wouldn't need to know how to use context, right? It would just basically be looking for a match out of all the data points it's seen before, and then outputting the next word, which some people have also posited as what they're doing anyways.
Yeah. Given
my work, I do believe that models generalize, and like I've seen very compelling demonstrations of strong in-context learning in transformer models. I think the danger is if you overtrain these models, it might actually go away.
Okay.
And then that would make these models less useful, even though the loss is lower.
Interesting. This is probably completely unrelated, but I remember once in SWC we had this debate about whether we are just using overtrained mice in like our actual context.
Yeah.
So could this be like a correlate in that, like, well, now the model is just overtrained.
Exactly.
And it's not actually representative of what we think it's doing.
Yeah, I think there's some analogy there where, like, once you overtrain it, it might not be acting in, like, the natural way, right? For models, there's not as clear what the natural way is. It's more the way we want them to act. And here the analogy would be that overtraining might lead them to act in ways we don't want them to.
Yeah. Yeah, I like how you said it, like, it goes away and the desired strategy is lost, but we want to keep it that way. So yeah, you're trying to understand why it happens in the first place, like, which you would have taken for granted maybe if it hadn't gone away after all that training. Yeah. But maybe we should dive a bit more into like what in-context learning really means in the context of deep neural networks.
Yeah, so in-context learning is this ability of like typically when you train a network, you're training it to do some task, right? And then at test time, you test it on that task. If you test it on other tasks, it usually doesn't work well, right? So in-context learning is this ability that at test time, right, once you finish training your network, updating its weights, you now give it a few examples of a new task, and then it's able to perform that task. So what that means is rather than the network learning to do a specific task, it's kind of learned how to learn to do tasks. And so one of the reasons we found that language models might gain this ability is this thing known as burstiness in natural language, where let's consider a rare word like, I don't know, neuroscience, relatively rare on the spectrum of all words in the English language, right? When you see the word neuroscience on a web page, you're probably going to see it many times on that web page. So if like the overall frequency of the word neuroscience is like, I don't know, 1 out of 10,000, but it's not going to be uniform across all documents you read, right? In some documents it'll be way higher, and some documents it'll be 0. So that's known as burstiness. Like when a word appears, it appears more often. And so when you train on natural language data, which has this bursty property, the network learns to kind of oh, I should like, instead of memorizing how often to use the word neuroscience, I should rely on how often it's been used so far and then use it more if it's been used. So that's like a very naive example of in-context learning. Cool thing is that obviously models can obviously do that, but then they end up like, you can teach them like completely new things, right? Like, I think one compelling demonstration to me was like, even in the first like GPT-3, which is kind of what spurred the language model revolution, like the model just figures out how to do addition, even though it hasn't been trained on any addition problems or taught the algorithm for addition. You give it a few examples and now it can do addition. And then some people were like, oh, like, we don't know if we believe this. If you make it do like 10-digit addition, it's not able to. And then there was this really cool paper which showed that like, if you just take like 2 to 3-digit addition problems and actually write out the algorithm, and then you prompt it with a 30 plus 30-digit addition problem, it can like apply the algorithm, even though it's never done 30 plus 30-digit addition, right? And it's never seen the algorithm described in this esoteric way, but it's still able to compose the two, which I think is super cool.
Yeah. Wow.
I heard that ChatGPT uses Python to do maths.
Right. So
Yeah.
that's this kind of newer development in the language modeling field called tool use, where basically the model is now given access to use tools, and then it can query the tools. And so GPT models can do math without tools, but they also, like, if you're using the chat.openai interface, it will probably call a tool, because then it's going to get the exact answer. But what's cool is often for tool use, right? Like, for things like using a calculator, searching the web, it's relatively easy to generate data and then train the model to use these tools. But even within tool use, there's an application for in-context learning where, let's say you're at a company and you have some internal tool that you now want your language model to interface with. You can't really train it on that tool, right? Because, like, do you want to give OpenAI your tool? Not really, right? But even for tool use, you can often teach it how to use the tool in context. You kind of describe the tool, you give it a few examples, and then it'll start using the tool. And so that's, in some ways, easier for enterprises as well, right, to use the model.
Interesting, yeah. So before we started, well, when we were researching for your episode, you sent us this paper on what needs to go right for an induction head. Can you tell us a bit about this?
Yeah, sure. So that's this new paper that'll be out soon publicly on looking at for in-context learning, right? Similar to kind of how when we have some behavior that a mouse or a human is doing, we try to identify what brain area, right? Or like what circuit might be implementing that. So there's this field in machine learning called mechanistic interpretability that tries to do the same thing, where they look at these networks and they try to identify the circuit that's implementing a certain behavior. And so for in-context learning and language models, some people at this company called Anthropic identified the circuit called the induction head, which is actually performing this computation. And so they identify the circuit and then they kind of describe it, and then that's about it, right? Which is still like really good, right? And really important to know. But then given our work kind of on how in-context learning sometimes goes away, trying to figure out why it appears, we thought it would be cool to look at the dynamics of the emergence of this circuit, right? And so as I mentioned at some point, I think these circuits tend to appear in what's known as a phase change, where kind of the circuit's not there at all, and then all of a sudden it's there.
Wait, when you say circuit, what do you mean?
Right, so an artificial network is kind of made up of neurons, right?
Okay.
Or like computations. They're not biological neurons, but it's kind of similar, like there's one computation that gets repeated a bunch of times, right? And layered on top of itself. And so a circuit is similar to like how you might find like a set of neurons implement something in the brain. Here it's like a set of artificial neurons that are implementing this computation. So if you were to ablate those, the computation would go away, right? If you were to replace those with kind of the exact version, you would get higher accuracy and stuff like that.
But is this a circuit that you've like constructed, or you said emergence?
Yeah.
So it
when
happens
you
spontaneously?
train the network on some data set like natural language, right? Then the circuit just emerges.
Okay.
Yeah.
So
Oh, cool.
As someone who can't help but see it from a neuroscience perspective and is kind of struggling to understand the physicality of this, this neural network, how do, like, doesn't that, if the circuit emerges, does that mean that the number of neurons in the artificial network increases, or are they more connected?
Yeah, it's changing the connections, right? So when you learn in a neural network, you're basically updating the synaptic weights between these neurons, right? Yeah. So how they wire together. And so what I mean by a circuit emerging is now the weights have reached values that create this computation through like composing various neurons. Yeah.
Okay, so do you have to set the parameter of how many neurons there are to begin with?
Yes, yeah. So typically at the start of training, you set the architecture, and then all that changes are these weights.
Okay.
Yeah.
And the architecture is set based on the number of basic computations?
I guess, yeah. So typically you just choose like what types of neurons, so to speak, you'll use. So for transformer models, there's kind of standard multi-layer perceptrons, which are like weighted sums of the inputs. And then there's this other piece called a self-attention layer, which is this like, probably hard to describe, but this computation where basically it basically looks at relational connections between inputs.
Okay.
And the way it forms those relations is dependent on some weights it has, right? And so then you basically just stack these two. So you'll have like a layer of neurons that are doing self-attention, then a layer of neurons that are doing MLPs, and so forth.
Yeah. And
so you'll specify the number of layers, how wide the layers are, stuff like that at the start of training. And then all that are these weights between the neurons. Okay. And so going back to emergence, what I mean there is like when an induction head emerges, that means the weights are now set in a way to perform the stereotyped computation robustly.
But how dynamic is the induction head? Like, how long does it last? And is that related to this loss of function that you described?
Exactly, yeah. So we're still digging into like the understanding of this kind of transience of in-context learning. But so far what we've seen is actually you do see these induction heads show up briefly, and then they go away. Okay. Which is very fascinating.
Yeah.
Which hasn't been seen on language models yet, as far as I know, perhaps because they haven't been trained long enough. There is some work, though, that's consistent where, for example, with models, you typically, like we said earlier, right, you pick the size at the start. And so when people are training these large models, you pick the size of the model and you pick how long you want to train it, right? But typically what you're limited by is actually like how much money you have or how many GPUs you have. Yeah. So if you pick a larger model, you can't train it as long, right?
Yeah.
And so then there's this cool paper which shows that smaller models don't do in-context learning as purely as larger models. And so you could say, oh, that's just because of scale, or maybe it's because the smaller model is actually trained for way longer relative to its size than the larger model. Yeah. Right? So, of course, to test this, I would need to be able to train a large model, which I can't do. But the finding is consistent with, like, large-scale results like this. Yeah.
And, sorry, just to clarify, so induction head is what you called this type of circuit?
Yeah, the circuit that implements this in-context learning computation.
Okay.
Yeah.
Okay, yeah. I'm loving the continuous comparisons between, like, deep neural network stuff and neuroscience stuff, and like, is it perhaps that like smaller organisms simply can't like input context? And,
like, I was literally thinking just like babies versus adults.
I was thinking more like Drosophila and C. elegans versus humans and mice.
Well, it's actually interesting because there are some theories, although very like not evidence-based, but about like certain properties emerging in terms of seizure activity, for example, in just smaller organisms that, like, it doesn't emerge in smaller organisms, but it does in larger organisms. So as just a function of size, which we would think is just, like, too simplistic to be able to define things, just the size, like, physical.
Yeah.
I guess that's the thing that neuroscience kind of lacks, is, like, a conception of physicality, because we're so obsessed with, like, the biology.
Yeah. It's really interesting.
That's where these sorts of conversations help. So what needs to go right for an induction head?
Right. So
after the title. Well, I guess maybe you can give us a sneak peek.
Yeah. So basically the work takes this kind of circuit that people have found, and then we really dive into like figuring out the details, right? So some of the interesting results, like we start off like everyone else just looking at end networks. The first thing we found is that, which had perplexed us going in, is often networks will have multiple induction heads. So like multiple copies almost of the same circuit, and then it's just like, why? Right? Like,
yeah.
And so in our work we find like,
can you remove
exactly, yeah, you can. And so that was the first thing we did. We were like, okay, well, we have like 7 copies of this circuit. What if we just kill 6 of them? And it turns out that they're actually different strengths. And so like, if you remove all but the strongest one, performance is barely affected. But on the flip side, if you just remove the strongest one and leave the other 6, performance is barely affected. So they're like working together.
Yeah.
And in like an additive fashion, which is kind of cool, but also not necessary per se. And so it's also interesting as like this kind of emergent redundancy, right? Like there's no reason for the network to learn copies per se, right? We're not using any regularization. And so to that end, we actually connected to some work from Andrew's group on this method called, or like this idea called the neural race, where the idea is kind of, when you're learning this deep neural network, which has so many neurons, actually what's going on is you have a bunch of different like subsets of neurons that are racing each other to solve the task. And then what we found is actually, or like we have some preliminary evidence, I should say, towards the fact that the strongest head, like the strongest set of neurons for an induction head of the multiple copies, is actually the one that, if you trained it on its own, learns the quickest. And then in terms of why the other ones show up, we suggest that when you train with all the copies, you can learn faster, is what we see empirically. So somehow, by learning copies, the network's more quickly able to learn the task. Which again, we're not sure why exactly, but I think even that first step is interesting. So that's kind of the first half of the paper. And the second half is digging into this phase change, or the fact that these induction heads show up all of a sudden. And so there we kind of take inspiration from theory, which kind of a simple toy model of phase changes would be like, if you're trying to learn 2 vectors, if you minimize their the loss on their values based on their outer product. So that's kind of like if you have a vector of dimension 10 and then a vector of dimension 5, the outer product would be like kind of all 50 possible like multiplications. And so when you learn in that system, you actually reproduce this phase change. And the reason behind that is, let's say the vectors are A and B, to get them to their true values, you need them to both be close enough to then reinforce each other. Because if B is, let's say, super far from its value, since you're only learning using the product, you don't get any signal to learn A at that point. So let's say, you know those toys that babies play with, where they have to put there's like a square, a triangle, and a circle? Yeah. They have to pick up the right block and put it in the right thing. Right? And so let's say you tell the baby, put the square in. The baby needs to know what a square is, and it needs to know how to align the square to the hole, right?
Okay.
And if it has no idea what shapes are, no matter how good it is at aligning to the hole, it's not going to be able to learn.
Yeah.
And vice versa, it might know what shapes are, but if it's not good at aligning to the hole, it'll never be able to learn.
Yeah.
You need both of them to go right to kind of reinforce each other, right? And then once the baby has a slight idea of what the right shape is and a slight idea of what the right hole is, all of a sudden it'll make really quick progress. And that's basically the behavior we see in these neural networks, where an induction head is composed of all these different things that need to go right. And we see that we can actually decompose into these 3 sub-circuits that are all interacting. And what's cool is similar to, again, the baby example, where if you didn't have this kind of 2 things need to happen, if the baby was just trying to learn shapes, you can imagine it would smoothly learn the shapes, right? And so similarly here with these sub-circuits, on their own, they're smoothly learned. But when you're trying to learn all of them together, you get this very sudden phase transition. And the reason this understanding is useful is these days with language models, many people are using them. We train these models for a long time, and we don't really know what abilities they're going to have and what abilities they're not going to have, especially because so many abilities emerge in phase changes. And so the only way to find out is train a network see when the loss suddenly drops, and then you're like, oh, now it has the ability. But by understanding these subcircuits, you can look at how the subcircuits emerge on their own, which is way cheaper. It happens very quickly on its own. And then you could speculate as to, will you see a phase change? When will the phase change be? And so on. And so we kind of demonstrate that for induction heads. Obviously, future work could extend it to other circuits that emerge in a phase change. Yeah.
Very interesting.
Yeah, that's really cool.
So, just because I'm unfamiliar with it, basically, what's the n number? Like, how many times do you have to repeat this, and how stable is that over time in terms of how long it takes to get to this phase change?
Right, so what do you mean by what's the n number? Or
Because, like, how many, I guess in this case it would be trials, but in n number in terms of, like, how many times have you shown it?
Right. Yeah. So the way current models are often trained is actually no sequence gets shown twice.
Okay.
Like every sequence is different.
Yeah.
But they'll kind of be based off the same words.
Okay.
Right? Similar to language, like every sentence you see, like you probably haven't seen it before, right? But it'll use the same words. And so in that sense, like, yeah, the phase change when everything's being learned together, right, can take like 10 times as long to occur as if you were just looking at one of these subcircuits on its own.
Okay.
And so in that sense, you could predict how, like, if you change the number of words in your language, how will the phase change move?
Yeah.
If you just train the network, you'll have to wait a long time to see when the phase change happens. But if you look at the subcircuits, you can kind of predict that way quicker.
Okay, yeah. But I guess I was wondering, like, how input dependent is it? Because you said you give it different word sentences each time.
Yeah.
So does it vary? Do the timings of everything vary a lot, or is it quite reliable?
Well, since the data distribution is like static throughout training, the main source of variance is actually the network initialization rather than the specific sequences it sees.
Okay.
Yeah. It's interesting to me that you said, I'm paraphrasing, that you'll train the networks and then you'll have these emergent circuits, and when you train a network, you don't really know what it's gonna do sometimes.
Yeah.
Yeah, I don't know. I feel like that will raise a lot of questions in people's minds, but also, and in terms of like the capabilities of these deep learning networks, I kind of imagined as scientists you would have like complete control over it. Yeah, so
I mean that is one of the big reasons AI safety has become such a huge field, is because of these emergent behaviors. I mean the biggest concern is obviously, like, what if one day it just decides it wants to like kill us all or something, right? Yeah. I don't really see that happening anytime soon, though some people would argue the other way. I think the risky behaviors that we should be looking out for more are like things like bias, right? Like some biases might emerge at a certain scale, and then if you don't realize that that bias has emerged, suddenly you've deployed a model into the world that is then propagating this harmful bias, right? Especially if it affects like only a subgroup of people and then like this ends very poorly. And so to that end, like, what do people do? They go through this, like, they call it red teaming process, where basically whenever you train a model, you just have a bunch of people try evaluating it, like talking to it, right, if it's a language model, to see if they can elicit all these harmful behaviors. When you train your new model, this sounds very bad, but it's like, you don't know. Like, the new model might be more harmful than the old model, and this often does happen, right? I think one example that I'd heard at one point, this was a while back, but like people have surely used like Gmail has an autocomplete feature, I think, right? So there was a startup I was interviewing for, and the person who was interviewing told me that apparently when they first started deploying this autocomplete feature, like, I don't know, like 8 years ago or something, there was this very harmful bias in the model of, like, if you were talking about a doctor, it would use the pronoun he.
Okay.
And nurse, it would use she, for example, right?
Yeah.
And so...
but interesting, because, like, what is that based on? What information has it been fed that led to this bias?
So it's trained on just internet data, right? And so if a bias exists in the internet, it'll pick up on it. But the reason it might interact with scale is a smaller model might just not pick up on this correlation, right? So the smaller model in that case would be less biased than the larger model. And so in practice, when this happens, then all the researchers are like, oh crap, now we have to fix it. So I think in this case, I don't have any personal experience with this story, right? This is just what someone told me. But they told me that what they did is actually they went back to the training data and they just took out all the pronouns.
Okay.
Because then that way you get rid of the bias, right? And so what I'm trying to say, though, is oftentimes, even with these large models, you only see the model they release. Oftentimes, there are many other capable models that they weren't able to release because those models were not safe enough. Which is, they were still expensive to train, like costing millions of dollars, but I still think it's better to, not release the unsafe ones.
I still think it's interesting about, every time I think about this, it seems like ultimately, though, it's constrained by the information it's fed, so, what it's trained on. And so when people say, the dangers of AI, it's well, the most dangerous it can get is basically reflecting reality. So
so that is current systems to some degree, I agree, but I guess reality can be pretty bad sometimes.
And it can reflect the reality of a dystopia basically, and then create that. So
and then on the flip side, there's also a lot of work for good purposes as well on self-improvement these days, where once you train the model, now you have the model generate outputs, and then you'll train on those.
Right.
So obviously there you can start departing from what humans have written, right? Because the model could develop its own thing, which is useful for things like, for example, if we want an AI that can solve really difficult scientific problems that we haven't solved yet. We'll need it to be able to figure stuff out on its own. But then on the flip side, this comes with a lot of risk, right? Where now if the model is kind of training on its own outputs, it might develop capabilities that are beyond human and harmful instead of and helpful. And so it's a really hard balance to navigate. And I think different companies have been taking different approaches to this, but
So in terms of learning strategies, and what is your opinion on, I guess, the best way to train a model given all that you've seen, and taking into account that dip that you have in the end, and I guess also taking account what you've learned with board games and how to teach neural networks these different strategies?
And to add to that question, just thinking about generalization, the ability to generalize and how important that is, what has this taught you about how generalization can help in different contexts of games, but how also different games require different strategies,
So I'll say two pieces on this kind of, right? One is kind of the prevailing view in the field, and then, which is obviously quite convincing because everyone does that, and then maybe how we might want to move away from that in some ways, right? So currently in machine learning, the main technique is just you have a lot of data, you have a model, and you minimize loss via gradient descent, and you just do this kind of blindly in some ways, right? And the reason this is so effective is because it's very easy to optimize, and so you can just show it so much data, and then we don't really understand why, for example, things like in-context learning emerge, but it just turns out when you show it all the data, it learns useful things. And so in that way, a lot of people argue that there's no point in working on anything else, you should just scale, right? You should just work on improving the performance and the speed of training and getting more data, and then we're just going to end up solving everything that way. I don't necessarily agree with this take. So some things that I think we can bring over from the human side of things, which it's interesting because it could be that networks are already implicitly doing this, and maybe helping them do that a bit more might help certain circuits emerge earlier or certain circuits stick around, right? In context learning. And so one thing I think about a lot is this technique, or more theory in cog sci called representational redescription, where basically it's this idea that the way humans might be forming concepts is you have some like past experience, right, and representations of it, and then what you're doing is you're just trying to compress those representations. So you're reflecting on your past experience, and then you're reorganizing it in a way that's more compressed, and that's how you end up forming these concepts. And there's like a lot of like kind of tangential things showing this. And
is that kind of like abstraction? Like,
yeah, it's a form of abstraction, exactly.
Okay,
yeah. And so, but I like it because it's a bit more specified on how the abstraction is happening.
Yeah.
And so what I think is really interesting is nowadays one of the main views on why machine learning systems generalize so well, an argument used by like Ilya Sutskever, who's the like lead researcher at OpenAI, is actually that the model is doing very advanced compression. So I think there are some substrates like this that match, right, across the fields. The question then becomes like, okay, how do we maybe bring them closer together, right? Like, how can we take these notions we have maybe from human intelligence and apply them crucially in an efficient way to artificial networks? Because I think a lot of neuro-inspired learning algorithms currently are way, way, way slower than gradient descent. And so then the issue becomes is like, given the same amount of iterations, your algorithm might do better. But if your iteration takes 10 times as long, nobody's going to use it, right? And so I think that's where the tricky part comes in. And then I guess I don't have an answer to that yet, but I'm hoping to, like, by better understanding the learning dynamics across agents versus humans, hopefully, and then also like with the context I have from a lot of the industry experiences, the goal would be obviously to develop learning algorithms that are more efficient, both in terms of the number of iterations and also the cost of each step.
Yeah, because I mean that sort of addresses what I was gonna ask, which is, can the artificial networks do it? Can they come up with solutions that are better than human learning?
Yeah.
And then you said the thing about speed, but are there any other ways in which it's better?
Yeah, so I mean, I guess a good example would be like the best chess networks play better than humans, right?
Yeah.
And that's very much because, for example, for chess, we train a network by having it play against itself. And it's just that it's so quick to play against itself, right? Because we can run that on a cluster and really scale it up. And it's like, if you could take a human and have them live thousands of years of chess games, then I think the human would be better than the network, right? It's just we can't scale the human up. And that's really going back to this, like, the reason people in AI and machine learning rely on these simple algorithms is because they've found that scaling better is just more effective to develop superhuman intelligence than learning smarter, which is kind of sad, but it's the current state of the field. Of course, I think the goal should be that you want something scalable that learns smartly, right? And I think
to combine them both, basically.
Exactly. And I think the issue there is just like there's not enough crosstalk, honestly, between people, because I think often like hardcore deep learning people think that neuroscience isn't perhaps as relevant, right? Because it's slow. And then I think a lot of people who are more on the computational neuroscience side are like, oh, like those people just want to scale.
Yeah.
And I think it's really important to, like, instead of looking at the negatives of the other field or the things you don't like about them, instead focusing on like, what did machine learning people do right and what did computational neuroscientists do right? And let's put those two things together, you know?
I really like that perspective.
Yeah, me too.
Yeah, and you sit perfectly in the middle, so...
Hopefully. That's the goal,
Yeah.
The main thing is just, I think, not enough people look at learning dynamics and looking at where the strategies are coming from, focusing too much on what strategies occur. And I think there's, in neuroscience, I think it makes a bit of sense why it's been difficult to do this, just because we have each lab has its own way of training the mouse, right, to do the task and stuff like that. On the AI side, I think there's a really nice opportunity because the algorithm is so standardized that, and because of how cheap it is to like save intermediate checkpoints, like it's hard to save snapshots of a mouse, right? Because the next day the mouse is different. With a neural network, you can just save the weights after 1 day of training, after 2 days of training,
nice.
and so forth. Yeah.
Freeze time.
Exactly. Another thing.
You don't lose any progress when you go away on holiday for a week.
Exactly. Yeah. And compared to humans, like, I know one issue with human experiments is often if you test the human, you're going to change their learning.
Yeah.
Right?
Yeah.
But with deep neural networks, you can just have the frozen version that you test and have the version that's learning. And so I think, especially on the machine learning side there, we have a lot of opportunity to study these learning dynamics. There's already been people who look at learning dynamics in humans to some degree. And so I think that can start motivating some hypotheses for machine learning systems. And then I think the really cool part will be once we start understanding the machine learning systems better, maybe there are hypotheses that we can carry back and then create better experimental paradigms for humans. And so that's, people often refer to this as the virtuous cycle, which has occurred to some degree on end networks. For example, in computer vision, people found this filter that neural networks learn where they'll look for like high frequency like texture on one half of the image and low frequency on the other half. And then like I think just a few months ago, neuroscientists found similar neurons in monkeys. Right? So similar to how you have like orientation filters, right? They have these high-low frequency filters. And so I thought that was a cool way that the line of work in AI that found these took a lot of inspiration from neuroscience. Then they found these new features, and then neuroscientists were actually able to reproduce that. I think it would be really cool if we can do that for learning dynamics as well. Like, I've worked on kind of understanding these sudden emergences of strategies, right? Humans also do this. Is there some way, I don't know what the experiment would look like, but maybe on mice or humans, that we could also decompose into like the subcircuits that are being learned and how that influences these sudden emergences that humans have, right? That'd be cool.
That'd be super cool.
Yeah.
I kind of colloquially see that a little bit with the mice that I train, where all of a sudden it's like, they get it.
Yeah.
But yeah.
I've never had the luxury of training mice.
It is a very luxurious life indeed.
I don't envy you.
But I thought as you were speaking about, you know, with human or neuroscience data, there's two quite distinct types. There's behavioral stuff and neural activity stuff. So what you've spoken about before about the representational redescription, that is based on human behavioral observations, no?
I think so, for the most part. Yeah, like from Conc Sci people, yeah.
And I guess like that sort of data is useful to formulate hypotheses on learning strategies that can be brought into the machine learning world. But what about comparing neural activity with the dynamics in these machine learning? Because it's weird that, like, you know, humans exhibit neural activity and then we exhibit behavior, and everyone does the most they can do to correlate the two. But with machine learning, you've got like both, like the behavior of the neural network is the behavior. Yeah, so I think there's like kind of four pieces, right? There's like neural representations in humans and human behavior, and there's representations in neural networks and the neural network's behavior, right? And in a neural network, it's easier to understand that connection from representation to behavior, just because you can literally go in and put in numbers for representations, right? And you can see how the behavior changes. For humans, I think like, or like for mice, like optogenetics and things like that have really pushed forward that connection as well. In terms of connecting the two fields together, there's a lot of interesting work in the fields of like looking at, like, for example, correlating fMRI of people listening to certain sentences with representations in large models as you feed in the same sentences, right? And so I think there are some interesting connections there. It's just difficult because you very quickly get into like a lot of multiple comparisons issues. Yeah.
Where like you have like all the voxels, right, from your fMRI, and then you have all the neurons in your neural network, or layers, or whichever granularity you choose. But like our largest neural networks today are like trillions of weights, right? And so there's like billions of neurons in there.
Wow.
And then are you going to correlate every neuron? Well, obviously some will match, right?
Yeah.
You could do a different granularity, but then what's the right granularity? There are a lot of these questions which I'm not saying there isn't an answer, but it's like it's difficult to answer them, and they would need to be answered in order to boost confidence in those correlations.
It would be interesting if you could manage to see some sort of parallel between both on the behavioral level and at the neurodynamics level?
Yeah, so to that end, like, one of the people I've worked with a lot at DeepMind, Andrew Lampton, he works a lot on this, and I really enjoyed my conversations with him where he's worked on both the behavioral level, where he's done some work on, like, if you give language models and humans a logic problem, right, and you frame it as a logic problem, right, they'll have certain accuracy. But now if you ground that logic problem in a real world setting, like you walk into a bar and you see like 2 people doing this and 2 people doing this, like what should you do kind of thing, then both humans and language models actually do better on the grounded version. Mm-hmm. So that's like kind of content effects on the reasoning, right? And so I think that's an interesting connection in the behavior. It could be interesting also to look at how the representations in those cases. For that, you would need humans to do this task in an fMRI machine and then connect the two. I don't think anyone's done that yet, but it would be really cool to do.
Yeah, and of course also, like, I'm always thinking, throughout this episode, I kept thinking, like, I wonder if there's a neural correlate in the brain of the induction head.
Right.
We have circuits, and we have strengths of circuits in different contexts, and but I don't know if there's, I mean, there is the idea of, like, this is more for long-term memory consolidation of, like, memories moving from being represented in the hippocampus to being represented in the prefrontal cortex, and then there's more of, like, it changes but like you form a representation of it at a higher order level. And so it's confusing,
Yeah, I think for my personal take on things like induction heads is that the circuit, like, some representations at, like, a certain level abstraction I think might be similar, but I think at lower levels it starts being really kind of related to the hardware you have, right? Like the specific computations that your neural network can do in terms of each neuron versus a biological neuron, right? And so there, I think if for some circuits like induction heads, it is like quite grounded in the specific computations that neural networks do, or transformers do specifically. And so because biological neurons don't do those same computations, you might not see the same structure.
Yeah. Like backpropagation.
Yeah, so that's like a learning rule that we use for neural networks, and there are a lot of people who work on it in neuroscience, I think, to see if it's happening, but I think there's like different ways of approaching that question, right? One is trying to like find a neuron that's implementing this, which I think can be difficult. I'm not well read on that literature, so take this with a grain of salt, but I don't think anybody's found such a thing. But then some work that Andrew's lab does, for example, that's very compelling, is you can show that learning via backpropagation in a neural network, if you look at, like, for example, how the representational similarity between different inputs changes over time, and you compare that to the representational similarity changes in a human learning a task, you might be able to find some correlates at that level, which would mean that it's not necessarily that the brain is implementing backprop directly, but its general learning dynamics are well modeled, perhaps. I don't think this has been shown, right? But like, I would say that would be an approach that might be more fruitful or possibly lead to finding a similarity.
Yeah, but what I find, like, obviously I don't expect there to be actually like correlates all the time, but and I find it so interesting how there could be that diversity, like there could be multiple different strategies, I guess, of networks to learn information, and it's just interesting to have an understanding of all of the possibilities that could result in this emergent behavior. Yeah. Regardless if it's what the brain does or not.
Yeah, definitely.
On that note.
Thank you so much for joining us, Aditya. It's been so enlightening learning about all of these different strategies that deep neural networks have.
Yeah, thank you so much. It was really enjoyable.
Yeah, thanks for having me. It was great.
Thank you so much for listening to today's episode. We hope you enjoyed it, and feel free to check out our social media pages on Instagram and Twitter at neuroverse_pod and our website neuroversepod.com for more information and resources.
Today's episode was made possible thanks to the support of the Sainsbury Wellcome Centre Public Engagement Fund. We would like to thank Sainsbury Wellcome Centre for the generous grant supporting science communication initiatives like these.